Hi everyone, we're back with another video today. We're solving chemistry paper 1 multiple choice. Chemistry paper 1 multiple choice. The paper is 9701, paper 1 2, and it's from the February March 2024 series. We have a time of 1 hour 15 minutes. There are 40 questions in this paper, and all of them have 4 options, out of which 1 is the correct answer. So before we dive into the threshold, I quickly wanna talk about my Patreon. If you guys like my content, please consider subscribing to the channel, as well as liking the videos, sharing it with your friends. It helps with the algorithm a lot, as well as supporting me on Patreon. It's CAIE Papers or patreon.com/CAIE Papers solved. We currently have 3 tiers, one for general support, the second tier, which is the most popular, where you get access to one-on-one problem solving sessions over text, where you can send your problems, I'll solve them. And you also get access to all my notes for AS and A2 physics and chemistry, as well as all the solved question papers for physics, chemistry, and bio, paper 1, 2, and 4 and 5, actually, as well as the solved question papers for math, pure math 1, pure math 3, statistics S1, and mechanics M1. And for the highest tier, you get access to all those perks, as well as a one-on-one video meeting with me via Google Meet, where we solve your personal problems once or twice a month, as well as a shout out at the end screen for all my videos. So if you guys do like the content and you think I can help you get better grades for A levels, you can consider supporting me there. So let's talk about the threshold, shall we? So take a look at the threshold. Here you go. So we're solving component 1, 2 over here. The maximum raw mark available is 40. And A was at 30 out of 40, B was at 27, C was at 22, D was at 17, and E was at 13. Okay. So A star should be at around 33 or 34. Considering the mark difference between each grade, it's around 3 or 4 approximately. So assuming that stays constant, A star should be at around 33 or 34, somewhere along there. Okay, anyway, let's start the video. We're starting with question 1 then. I actually have the paper solved because there was a problem during recording the video. There was an issue with the audio, so I have the paper solved, most of it basically. So don't worry, I'll explain everything though, so it's fine. Which species contains the same number of neutrons as carbon 14? Carbon 14, the isotope, and the same number of electrons as Na plus, the cation. Okay, so carbon 14. To find out the neutron number, what do you need to do? Mass number 14 minus proton number 6. We get 8 neutrons. And the number of electrons for sodium. So we know that sodium has a proton number of 11, but since it's a cation, hence we are going to lose 1 electron. So it has 10 electrons. So we're actually looking for 8 neutrons and 10 electrons, a species with those numbers. So let's see. So fluorine, it has 9 protons, and 17 minus 9, that's 8 neutrons. So it has 9 electrons and 9 protons, okay, and 8 neutrons, so it doesn't match. For B, this ion of nitrogen, it has 7 plus 3 electrons, which is 10 electrons and 9 neutrons, because 16 minus 7 is 9. This doesn't match either. And the neon, which has 10 electrons and 10 neutrons, so it doesn't match. So the correct answer must be D, this oxide ion. It has 8 plus 2 electrons, which is 10, and 16 minus 8 neutrons. So that's that. And piece of advice for you guys, usually, right, the trial and error questions tend to have the answer as D. Okay, so which process has the largest enthalpy change per mole? So let's take a look at the periodic table. So aluminium 3 plus, as you can see, aluminium is in group 13. Okay, so this is the fourth ionization energy. So the fourth electron, if we are considering aluminium, the fourth electron, 1 2 3. So the fourth electron is actually coming out from the second shell rather than the third one, so a high amount of energy will be required. Same for phosphorus. This is the sixth IE. Since it's in group 15, the sixth electron will be coming out from the second shell. So overall, all these, right, for sulfur, the seventh electron will be coming out from the second shell, and for silicon, the fifth electron will be coming out from the second shell, since silicon is in group 14. So essentially, what you guys need to understand is that all of these will have very high enthalpies. However, out of these, sulfur, the seventh ionization energy will be the highest. The reason being, all of these have the same electronic configuration, okay? Because after you take out the electron, they will have the same electronic configuration as neon, which is 1s2, 2s2, 2p6. However, it's just that sulfur has a greater number of protons, so the protons are attracting the electrons more strongly from the third shell, that last electron that's left in the third shell. As a result, due to this strong attraction, more energy is required to remove the electron. Does that make sense? Which is why the answer is C. Okay then, so for question number 3, which sodium compound contains 74.2% by mass of sodium? So as I said, this is a trial and error question. So the answer tends to be D. So I'm pretty sure if you just see a trial and error question and just mark D, like 6 or 7 out of 10 times, it's gonna work out. So if you're just if you don't have time anymore or something, just go for D. It'll work out. So the answer is sodium oxide, Na2O. As you can see, sodium has a mass of 23, the relative atomic mass, Rm. So 23 times 2 divided by 23 times 2 plus oxide, NaO, that's 16. So as you can see, it's 74.2%. The other questions are wrong. For example, sodium carbonate. If you try doing that, that's 23 times 2 divided by 23 times 2 plus 12 for carbon and 48 for 3 oxygen atoms. That gives you 43.4%, okay? So that's the gist. Number 4, what is the maximum volume of sulfur dioxide gas measured at room conditions produced from burning 100 dm cube of diesel fuel containing 0.8346 grams of sulfur? Alright, so the general idea is we need to form an equation of this diesel fuel. I named it as CXHYS. It is burnt completely in oxygen, and we will end up with sulfur dioxide as a byproduct along with carbon dioxide and water, but that's not our headache currently. We're just dealing with sulfur dioxide, okay? So the idea is we have 0.8346 grams of sulfur. So using that information, you can actually find out the moles of sulfur atoms, okay? So 0.8346 divided by 32.1, which is the RAM of sulfur, you actually end up with 0.026 moles. So the moles of SO2 will also be the same. The reason being, each atom of sulfur can bind with 2 oxygen atoms. So since we have the moles of sulfur atoms over here, we can actually find out the moles of sulfur dioxide. The reason being, each atom of sulfur binds with 2 atoms of oxygen. So if you have 1 mole of sulfur atoms, you're also going to have 1 mole of sulfur dioxide gas. That's the general idea. So now we have the moles of sulfur dioxide. This 100 dm cube was merely given to trick you guys. And then to find out the volume, we just need to multiply it with 24 dm cube. But since they want the answer in cm cube, which is why we multiplied by 24,000 instead. So yeah, we actually end up with 624 cm cube. So random life update. I actually joined the gym recently. It's been like 1.5 months. It's going good. I had leg day today, so I can barely stand. The effects are gonna get worse tomorrow. So which row shows the correct number of covalent bonds in a molecule of methyl propene? I actually wanted to start working out before, but I never had the time. You guys should work out too. It actually helps you sleep better, improves mental health, I guess. So which row shows the correct number of covalent bonds in a molecule of methyl propene? Okay, methyl propene. I drew the compound over here, methyl propene, as you can see. It's propene, but it's just that on carbon number 2, there's a methyl group as a side chain. So there's only one pi bond, okay? There's only one pi bond, which is this one over here. And all the other bonds are sigma. So this one is 3 sigma bonds, also 6 sigma bonds. Here there are 2, so 7, 8 sigma bonds. So there's another sigma bond here, 9. There's another here, 10. There's another here, 11. So 11 sigma bonds in total. Why did I say 3 sigma bonds here? Because it's CH3, right? So 1 sigma bond for each CH single bond, yeah? Number 6, aluminum chloride exists as a dimer, Al2Cl6, at room temp, and when it's heated to a high temp, the dative covalent bonds actually break, so it turns into a monomer, AlCl3. So the shape of AlCl3 is actually planar, trigonal planar, 120 degrees angle, mainly due to the fact that it is sp2 hybridized. It has 3 bond pairs, okay? But on the other hand, Al2Cl6, it's kind of like this, Al2Cl6. I'll draw it for you guys. Like this. So this chlorine atom over here forms the dative covalent bond with that aluminium. And this one over here forms the dative covalent bond with this aluminium. So as a result, it turns into sp3 hybridization with four sigma bonds. Okay. 4 bond pairs basically. So we know that the angle will be 109.5 degrees and the shape will be tetrahedral. Okay. So if you're actually interested in my teaching techniques, I'm actually going to launch a course soon for AS and A2 chemistry separately, which are going to be available for purchase. They will be pre-recorded videos, but it will cover the whole AS and A2 syllabus. So more information on that soon, and if you guys are interested, please do comment below. Then I'll try to roll the videos out faster. They'll be available for purchase on Patreon. So more details later. I plan to release the course for physics and chemistry for now, but if it gets a lot of reach, I might release one for bio as well as math. The table shows the physical properties of 4 substances. Which substance has a giant covalent structure? Okay, so clearly A and B are excluded. I crossed them out, the logic being the melting point and boiling points are too low for a giant structure. So it's between C and D. How to differentiate between giant ionic and giant covalent? The logic is a giant covalent structure cannot conduct electricity in liquid state. So the answer should still be poor. Okay, but ionic substances can't conduct electricity in solid state, but when they are dissolved, or when they're in aqueous solution, when they're dissolved in water, or when they are, in liquid form, right, they can conduct electricity. But giant structures cannot conduct electricity that well in liquid form, and they are actually insoluble in water, like SiO2, silicon dioxide, yeah, sand. Number 8, at room temperature and pressure, H2 is a liquid and H2 is a gas. So here, some of you guys just asked me a lame question. So you asked me, please explain the other options too, like why they're wrong. I do agree. You should know why the others are wrong and why the correct one is correct. But in questions like 8, rather than reading all the options and wasting time, you should just look for the correct answer, because you guys know that H2O has hydrogen bonding while H2S does not, which is the main reason why it has a higher boiling point, so, or melting point. So we're just going to look for that. There's significant hydrogen bonding between H2O molecules, but not between H2S molecules. That's that. Okay. So number 9, the enthalpy change for a reaction can be calculated from values of these. Okay, so this is a rather complicated question. So I'll explain why the others are wrong, but let's explain why B is the correct answer first. So you can either find this using the enthalpy of formation, combustion, or the bond energies. Okay. So if you use the enthalpy of combustion, this is how it is. This is the Hess cycle. So this is del HR, this is the main reaction, and you can either burn CH4 or you can burn C2H6. So here's how it goes. If you burn C2H6, that's the direct route to get carbon dioxide and water, and the alternate route is converting C2H6 to CH4 followed by burning CH4. Okay, so those two on top, this plus this plus this will be equal to this essentially. Okay, so if you draw the Hess cycle, it's if you equate it, it's basically del HR plus enthalpy of combustion of CH4 times 2 though is equal to 2 times the enthalpy of combustion of C2H6. So if you make del HR the subject, it actually turns into this 2 times del H combustion of C2H6 minus 2 times del H combustion of C2H4. Okay, that's that. So as you can see, it actually matches with option B over here. Why are the other ones wrong though? A is completely relevant because it also deals with combustion. Now about the bond energies, if you look at the bond energies, it's actually like this. So bond breaking minus bond making. So if you look at bond breaking, what bonds are broken? As you can see, 2 CC bonds and 6 CH bonds over here. 1, 2, 3, 4, 5, 6. But there are 2 molecules of this, so that will be doubled. It will be 4 and 12. 4, 12. And then 1 oxygen bond over here, but 3 molecules, so 3 oxygen double bonds. And then minus for methane, we have 4 CH bonds. This is bond making, but there are 2 molecules of methane, so 2 times 4 is 8. And then you have carbon dioxide, which is like this, 2 C double O bonds, so that's 2 times 2, which is 4 C double O bonds. And then finally for H2O, you have 2 OH bonds, but 2 times 2 is 4 OH bonds. So if you do the simplification, it's kind of like this: 4 CC, then 12 minus 8, which is 4 CH bonds. Then you have 3 oxygen double bonds over here, minus 4 CO double bonds, minus 4 OH bonds. So if you match with this, what can you see? That the numbers are wrong. As you can see, it should actually be 4 CC bonds, and then, you know, sorry, it should actually be 2 over here, right? It should be 2, my bad, sorry. 2 CC bonds, because we had 1 C single bond C, but since there are 2 molecules of ethane, it should be 2 times of that. So as you can see, the number is missing. It should be 2 over here, and 4 CH bonds, and the oxygen double bond is missing completely. That's also broken. They didn't mention that. So, and for formation, if you guys want to know about formation, let's take a look at formation. For formation, elements are down below. So carbon, hydrogen, and oxygen, and the arrows go up. So we have C2H6 plus 3O2, and then we have 2CH4 plus 2CO2 plus 2H2O. We have 2 over here. Okay, so we need 4 carbon, then 2, 6, 12, 6 hydrogen over here, and oxygen we need 3 over here. So the logic is, this is del HR, so his cycle should be like this. These two combined actually equate to that. So if I show you the correct working over here, it should be like this. So del H formation, 2 times del H formation of C2H6 plus del HR is equal to 2 times the del H formation of CH4 plus 2 times del H formation of CO2 plus 2 times del H formation of H2O. So that's that. So if you make del H are the subject, the minus sign should come over here. So this is what we're looking for. So if you look for this, you won't get it. Look, I'm looking for this. It's the 2 is missing. Clearly the 2 is missing. There is no 2 over here, which is why it's wrong. If you match it with the one I have on the right hand side, this is what I'm looking for. 2 methane, 2 carbon dioxide, 2 water, minus 2 ethane. You see that the numbers are missing. That is why it's wrong. Okay, so we are currently at question number 10. Which reaction has an enthalpy change equal to the standard enthalpy change of formation of propane? So for enthalpy change of formation, the key points are, you actually need to look at the standard states. Like hydrogen is a gas in standard conditions, carbon is a solid in standard conditions, it's not a gas. So it's between C and D, and propane is a gas under standard conditions, which is why the answer is C. For 11, one of the reactions in the rechargeable lead acid battery is shown, as you can see. Which statement about this reaction is correct? Okay, so look at lead. Okay, so on the left hand side, lead solid has an oxidation number of 0, and PbO2, the oxidation number of lead is +4. So on the right hand side, if you look at PbSO4, sulfate has a oxidation number of -2, so lead should have an oxidation number of +2. So lead from the left hand side goes from 0 to +2 as well as from +4 to +2. So from 0 to +2 it is actually oxidized, and from +4 to +2 it is actually reduced. So yes, lead is both oxidized and reduced in this reaction. Okay, moving on to question number 12. So this is basically a redox reaction. So the general idea for a redox reaction is you have to balance the number of electrons. Okay, so clearly iron 2 plus is oxidized to iron 3 plus, and the number of electrons transferred is 1. On the other hand, sorry, excuse me, manganate is +7 over here, permanganate, and it turns to +2, so a total of 5 electrons are transferred. So to balance the number of electrons, you need to multiply this by 5, so there should be a 5 here before iron, so Y should be 5, and there should be a 1 before manganese. X should be 1. Okay, next, 13, nitrogen and hydrogen are mixed in a reaction vessel. The reaction reaches equilibrium, giving a mixture of nitrogen, hydrogen, and ammonia gases. The mixture of gases present at equilibrium at a total pressure of 300 atmospheric pressure is shown. So calculate the value of Kp, the equilibrium constant, for the forward reaction. So the general idea is to calculate Kp, we first need the partial pressures. How to find out partial pressures? First find out the mole fraction and then multiply with the total pressure. So for ammonia, for example, NH3, the mole fraction is 160, the moles of ammonia divided by the total moles of gas, which is 930. I added all 3 up to get this particular value over here, as you can see. So for ammonia, the mole fraction is 160 by 930 times 300, which is 51.61 atm. And then for nitrogen, similarly, it is a 180 by 930 times 300. And for hydrogen, finally, it's 590 by 930 times 300, which is 190.32 atm. Now the expression for Kp, what will it be? It is always partial pressure of products by partial pressure of reactants. And for products, since there are 2 moles of ammonia, it will be the partial pressure of ammonia whole square divided by partial pressure of nitrogen times the partial pressure of hydrogen whole cube. Okay, so yeah, I wrote the expression over here on this side, and if you do the working in the calculator, you will get this as the final answer. Partial pressure of ammonia 51.61 whole square divided by the partial pressure of nitrogen 58.26 times the partial pressure of hydrogen 590, sorry, the partial pressure of hydrogen 190.32 whole cube. So that is the final answer. Okay. Moving on to question number 14. A mixture of hydrogen gas and iodine gas is placed in a reaction vessel of volume V and temperature T. The reaction is allowed to come to equilibrium. All substances remain in the gaseous state. Argon gas is then pumped into the reaction vessel. The temperature in the vessel is maintained at T. How are the rate of forward reaction and the partial pressure affected? So, rate is affected by a catalyst, presence of a catalyst, temperature, surface area, then pressure in the case of gaseous reactants. So since temperature remains constant, the rate is unaffected. And when you add argon into the container, right? So argon is not present in the right side or left side of the equation. So actually, argon does not affect the equilibrium. The proportion of hydrogen on the left hand side and the proportion of hydrogen iodide, hydrogen iodine on the left and hydrogen iodide on the right, will be unchanged basically, because the argon does not shift the equilibrium because it is not part of it. Okay, so the answer is D. Rate is unchanged as well as the partial pressure of hydrogen iodide because the equilibrium does not change. So yeah, we know that pressure is nRT by V, temperature remains unchanged, volume remains unchanged, R is a molar gas constant, it's constant, and N is the moles of hydrogen iodide. So since that doesn't change, pressure won't change either. Two experiments are carried out to study the reaction between zinc and sulfuric acid. Small lumps of zinc are added to excess dilute sulfuric acid, and then in experiment 2 the reaction is carried out at a lower temperature and with one other change. So let's try to figure this out. Both experiments produce the same total volume of gas and are completed in the same time. This is rather interesting because if you carry it out at lower temperature, the rate will be slow, right? So it's not supposed to end at the same time. So complete in the same time. Lower temperature means slower rate. So it should be completed at, it should take longer time. So we must have brought about another change which has increased the rate here. We might, add a catalyst, for example, which is why A is the answer. And I'll tell you why the others are wrong. So check this. Why is D wrong? D is wrong because if you use larger lumps of zinc, we have decreased the surface area, so rate would decrease. And you cannot use a greater mass of zinc. The problem with this is because we are getting the same total volume. So if you use a greater mass, since sulfuric acid is already in excess, we're supposed to get a larger volume, but they said we get the same total volume of gas. Okay, that's important. And a greater volume of sulfuric acid is added. That is actually irrelevant because sulfuric acid is already in excess at the beginning of the experiment. Yeah, so the general idea is temperature is lower, so it should have finished at a later time, but we have brought about another change which increases the rate, which is in fact adding a catalyst. Number 16, the relative magnitude of the property X of 5 elements is shown. P, Q, R, S, and T are all in period 3 and they have consecutive atomic numbers. The letters are not actual chemical symbols. Okay, so this is honestly electrical conductivity. I'll tell you guys why. Because if it was electronegativity, you guys know that as you go across the period, electronegativity increases. So it should have gone up like this. That's electronegativity. And it's not melting point because the graph of melting point looks like this. For the third period, it looks like this. Sodium, magnesium, aluminium, silicon has the highest melting point because it has a giant structure. Okay, then it dips down to phosphorus, sulfur, and chlorine, which are non-metallic. Sulfur has higher melting point because it exists as S8 compared to P4 of phosphorus. All right, so it is clearly the electrical conductivity. The logic being, magnesium has more delocalized electrons than sodium, and aluminum has more delocalized electrons than magnesium and sodium. It's Al3 plus, more electrical conductivity. Silicon is not a very good conductor, it's just a semiconductor, and phosphorus is a non-metal, so it can't conduct electricity, right? So that's why B and C are wrong. And second, ionization energy shouldn't be like that either, because look, ionization energy actually depends on the group. Yeah, so if you go across the period, like, it won't be that high for sodium. Actually it will be very high for sodium, because when you take out the electron from sodium, It's actually in the which shell actually? It's actually in the second shell. So it can't be sodium. Sodium will be really high. And for magnesium it will be pretty high, but not as high as sodium, because it's still from the second electron is still from the third shell, not the second shell. Anyway, the answer is A. 17. Element X is in period 3. It reacts with oxygen to produce a solid Y. Okay. When solid Y is added to water, a solution with a pH of less than 7 is produced. What is the identity of element X? Okay. So it can't be sodium, because sodium oxide, when dissolves in water, it forms an alkaline solution, not acidic. Then it can't be silicon, because SiO2 is insoluble in water. Now it's between phosphorus and sulfur. It's not sulfur, because although it forms an acidic solution, sulfur reacts with oxygen to form a gas, sulfur dioxide, which is why it can't be sulfur. So the answer must be C. Number 18, this question refers to isolated gaseous species. The species fluoride, neon, and the sodium cation are isoelectronic. This means they have the same number of electrons. In which order do their radii increase? Okay, so the logic is all of them have the same electronic configuration. Sodium, fluorine, and neon, it's 1s2, 2s2, 2p6. It's just that fluorine has an extra electron and sodium has one less electron. However, if you think about it this way, since they have the same number of electrons, which is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, the one with the greatest number of protons will attract those electrons the most. So sodium, it has 11 protons, it will attract the 10 electrons very strongly, so the size will be the smallest. And on the other hand, fluorine, the fluoride ion, it has merely 9 protons to attract those 10 electrons. So the electrons will actually repel and the size will actually be bigger. Okay, so that's the general idea, which is why C is the answer. Fluoride is the largest and sodium cation is the smallest. Okay, number 19. Separate samples of magnesium and calcium are added to an excess of dilute sulfuric acid. The observations are summarized in the table. So the general idea is, here we are dealing with group 2 metals and the reaction with sulfuric acid to form group 2 sulfates. So remember this forever. Actually not forever, just these 2 years of ASNA2. Group 2 sulfates, right? So I meant to say solubility decreases down the group. So barium sulfate has the least solubility, it's actually insoluble. On the other hand, beryllium is not considered in this series, actually it starts on magnesium. Magnesium sulfate has the greatest solubility. As you can see, it completely dissolves. Okay, so here we are actually talking about the sulfates after reaction with sulfuric acid. So the general idea is, this is a question on group 2. You will either get a question on group 2 sulfates or hydroxides. For hydroxides, solubility increases down the group, and for sulfates, solubility decreases down the group. So since magnesium sulfate is more soluble than calcium sulfate, which is why we get these observations. Understood? Next. Number 20. Dolomite is a double carbonate and can be used instead of calcium carbonate for treating acidic soils. The 3 statements all refer to agricultural use of these carbonates. Dolomite and calcium carbonate are both less soluble than calcium hydroxide. Of course, if you think about solubility, carbonates are insoluble except group 1 and ammonium carbonates. But calcium hydroxide is relatively soluble. It's a sparingly soluble salt, because hydroxide solubility of group 2 hydroxides increases down the group, yeah. But carbonates are insoluble except group 1 and ammonium. So 1 is correct. Number 2, 1 mole of dolomite has the same neutralizing effect as 1 mole of calcium carbonate. Wrong. 1 mole of dolomite has 1 mole of calcium carbonate as well as 1 mole of magnesium carbonate. So logically it should have at least like a double the neutralizing effect as 1 mole of calcium carbonate. That's the general idea. Like it's not exactly double, but it will obviously be more, right? Because it has calcium as well as a magnesium salt. On the other hand, number 3, So 2 is wrong, which is why options A, C, and D are excluded. So B must be the answer. And dolomite and calcium carbonate both increase the pH of acidic soils. Yes, it is used to treat acidic soils to increase the pH so that it reaches or approaches neutral pH, right? Number 21, this question is about two salts, sodium iodide and sodium chloride. The two solid salts are separately added to warm concentrated H2SO4 and the results are noted. Aqueous solutions of the two salts are separately added to silver nitrate. Okay, so you guys need to understand something. This is a question on group 17, halides. So, chloride reacts with silver nitrate to form a white precipitate which is soluble in ammonia. Bromide reacts with silver nitrate to form a cream PPT which is partially soluble, partially dissolves in ammonia. And iodide reacts with silver nitrate to form a yellow PPT, but it is insoluble completely in aqueous ammonia. So why did I cross out A and B? A is wrong because sodium chloride, okay, that's fine. It is a colorless solution. This is true. However, when it reacts with H2SO4, chlorine is not produced. Why? Because H2SO4 is an oxidizing agent and chloride is a reducing agent. I agree. However, H2SO4 is a weaker oxidizing agent than chlorine, which is why it does not have the capacity to oxidize chloride, because chlorine is a stronger oxidizing agent than sulfuric acid. So A is wrong, and there is no freaking way that we can get H2S from NaCl. That's the same reason, because chloride isn't getting reduced in the first place. Chloride isn't getting oxidized in the first place. It is remaining as chloride. And we do not get a white PPT. It turns into colorless. So C is correct. Why? Because NaI, right? It does react with constant H2SO4 because sulfuric acid is in fact a stronger oxidizing agent than iodine. So it can oxidize iodide to form iodine. And iodine is also produced, H2S is also produced. These are produced. So till now these are correct. But the correct answer lies over here, the yellow PPT. I told you guys that iodide forms a yellow precipitate with silver nitrate, which is insoluble in ammonia, yeah? Okay. The diagram shows the process of adding calcium nitrate and strontium nitrate to separate boiling tubes and heating them. Identical conditions are used, okay? So, another question on group 2 is group 2 carbonates and nitrates, the thermal stability. As you go down the group, the thermal stability of the nitrates and carbonates of group 2 actually increased down the group, okay? So calcium nitrate is actually above strontium, so it will actually decompose faster or quicker, okay? So that causes the quickest color change. Since calcium nitrate is above, calcium is above strontium, the change will occur quicker. It will decompose faster. And what will be the color change? Basically, nitric oxide is an acidic gas, okay? So the acidic gas will react with water to form an acidic solution. So the change will be from green neutral to red, which indicates a pH less than 7, acidic, okay? So that's C. We are at question 23 now. The equations for 3 reactions involving chlorine or its compounds are listed. Equation 1 describes the formation of a compound used to kill bacteria in drinking water. Not really. If we got the ion ClO, chlorate, ClO, chlorate 1, I don't get that. That's the bleaching agent actually. Since it's not there, it cannot actually kill bacteria. It's in bleaching powder. Equation 1 does not represent a redox reaction. Wrong, because look, oxide is -2 over here, right? And it turns into 0. It's clearly redox. Equation 2 describes the formation of potassium chlorate 4. So let's check potassium chlorate. So this is -8. This is +1 for sure, group 1. This is +7. This is potassium chlorate 7, guys. C is wrong. Equations 2 and 3 are both disproportionation reactions. What is a disproportionation reaction? It is a reaction in which the same species gets oxidized and reduced simultaneously. So here it's -6 +1, so chlorine is +5. It changes to +7. It went from +5 to +7, oxidized, and also went from +5 to +1. So oxidation as well as reduction. And for equation 3, look at potassium over here, it is +1. Yeah, it changes. Okay, no, we're actually looking at chlorine over here, my bad. So chlorine initially starts off at 0, but over here it turns into chlorine -1, and over here it turns into +1 -6 +5. So yes, it is also disproportionation. So yeah, 23D is correct. Nitrogen monoxide, NO, is a primary pollutant produced by petrol engines and is found in their exhaust gases, which reaction occurs in a catalytic converter and decreases the emission of nitrogen monoxide. So the general idea is the catalytic converter converts unburnt hydrocarbons as well as carbon monoxide. Okay, it actually burns them completely, and it converts nitrogen oxides to nitrogen. So nitrogen oxide monoxide will react with carbon monoxide to form CO2 as well as nitrogen gas, an inert gas. So we are looking for nitrogen monoxide and carbon monoxide on the left hand side, which is why I crossed out B and C. They have carbon dioxide. And on the right hand side, I'm looking for N2 and CO2. That's the general idea. Okay, so 24 is C. 25, let's do this. Okay, so cholesterol. Student X stated that the 17 carbon atoms in the 4 rings all lie in the same plane. This is actually wrong, because only this carbon, the sp2 hybridized carbons, they lie on the same plane, and at max these 2 carbons can also lie on the same plane, and maybe this one as well, but that's that. All the other ones, they don't lie on the same plane because they are sp3 hybridized. This guy is wrong, don't be like him. Okay, Student Y stated that this molecule displays cis-trans isomerism. Wrong as well. Yes, it is required. Carbon-carbon double bond is required for cis-trans isomerism. However, it can't be in a cyclical compound, which is why student Y is wrong. Yes, cis-trans does exist in a cyclical compound, but the double bond is not required then. That's a very specific case which is included in your course book. You can look into it, but I haven't seen a question on that yet. 26. The drug cortisone has the formula shown. In addition to the chiral centers marked with an asterisk, how many other chiral centers are there? I'll teach you a quick trick. Any sp2 hybridized carbon is already excluded because we need 4 different groups attached to a carbon atom to be chiral. And these are also excluded because these have 2 hydrogens attached to them. Okay, so these are excluded. Yeah. Okay, so these are not chiral, this is not chiral, this is not chiral, this is chiral. Okay, then this is chiral, right? And this one is chiral. And look, all the others are like, this is CH3, CH2, CH3. They have the same groups attached. So we have extra 3 carbons, which have chiral centers. Yeah, extra 3 chiral carbons. 27. Butene reacts with cold dilute acidified KMnO4 to give product X. Okay, so we know that cold dilute KMnO4 reacts with alkenes to form a diol. So this is the diol that we get. I drew it over here. And then butene reacts with hot concentrated KMnO4. So butene reacts with hot KMnO4. There will be oxidative cleavage, and we will end up with 2 molecules of ethanoic acid, because this carbon has only 1 alkyl group attached to it. And the rule is 0 alkyl groups actually amount to methanoic acid, which further breaks down to form carbon dioxide and water. 1 alkyl group results in a carboxylic acid, and 2 alkyl groups, I'm talking about the carbon that has the double bond. If it has 2 alkyl groups, it forms a ketone. So yeah, that's that. So both product X and product Y will react with 2,4-DNPH. This is wrong, because on one hand we have an alcohol, on the other hand we have a carboxylic acid. But 2,4-DNPH is a test for carbonyl compounds, ketones and aldehydes. Neither product X nor product Y will react with 2,4-DNPH. That is the correct answer. Okay. Next, a sequence of reactions takes place. The major product is compound Z. So propanoic acid reacts with the reducing agent lithium aluminum hydride. It actually reduces carboxylic acids to form primary alcohols. From propanoic acid we get propan 1-ol. And then it reacts with concentrated H2SO4, which is a dehydrating agent, to form an alkene. So water is removed from propan 1-ol to form propene. And then when we pass a vapor H2O gas with steam H2O gas with H3PO4 phosphoric acid, we actually end up with an alcohol. and the OH group will attach to the carbon which has more alkyl groups. So thus it will actually prefer carbon 2 compared to carbon 1, because it will actually form a more stable carbocation in the as an intermediate. It forms a secondary carbocation compared to the primary carbocation that is formed if we got propan 1 ol instead. So propan 2 ol is the major product. They said major product clearly. If they said minor product, the answer should have been propan 1 ol. 29, which statement is correct? Bromoethane reacts with NaOH to form ethene as a major product. If it was NaOH alcoholic, it would have been true. But since it's NaOH aqueous, it is actually going to be ethanol instead. It's actually nucleophilic substitution reaction, not elimination. Number B, 1-chlorobutane reacts more rapidly than 1-bromobutane with NaOH aqueous. No, the hydrolysis will be faster for 1-bromobutane because the C-Br bond is longer, so it's easily broken compared to 1-chlorobutane. The CCl bond is smaller and stronger. Hydrolysis of this compound, look at this compound, CH3, CH2, CH2, CH3, okay. So this is a tertiary halogen alkane. So it will actually prefer the SN1 mechanism because it's very stable. So this is also false. So what is this? This carbocation, this primary carbocation is less stable than this tertiary carbocation. Yes, that is completely true. This tertiary carbocation is more stable than that one because it has 3 alkyl groups, the carbocation. As a result, there is more positive inductive effect, which actually, reduces the electron or the charge density on the carbon, so it is more stable. So question number 30, in the hydrolysis of bromoethane, by aqueous NaOH, what is the nature of the attacking group? Okay, so hydrolysis of bromoethane, let's check this, come on. As you can see, bromoethane is this compound, CH3 CH2 Br. So this is del minus and this is del plus. So this is nucleophilic substitution, right, on a primary halogen alkane. So the attacking group is the hydroxidane, which will attack this carbon over here, the central carbon atom, and there will be heterolytic fission of this bond. And ultimately, we will get CH3, CH2OH ethanol, and the byproduct will actually be, the leaving group will actually be this bromide anion. So the attacking group is a nucleophile, and the leaving group is also a nucleophile. So that is how we get an answer of D. Alright? Alright, so for 31, X is an organic compound containing the elements carbon, hydrogen, and oxygen only. The table shows the observations made from 3 chemical tests carried out on X. So essentially, it does react with sodium, so it's either an alcohol or carboxylic acid. It reacts with sodium carbonate, so clearly it's a carboxylic acid. And then it does not react with potassium or dichromate in general, acidified dichromate. So it cannot be oxidized, it remains orange, it does not change from orange to green. So what are we looking for? We are looking for the carboxylic acid group, but it can't have a primary or secondary alcohol. So A, it does have carboxylic acid, but it has a secondary alcohol which can be oxidized, so this is wrong. B does not have a carboxylic acid, so it's wrong. C does not have a carboxylic acid, so it's wrong. D is the correct answer. Why? It has a carboxylic acid group as well as a tertiary alcohol which cannot be oxidized. So 31D makes sense. How many moles of oxygen gas are required for the complete combustion of 1 mole of this? Okay, so let's write this down. It has C4 in total, H3 times 3, 9 plus 1, H10O. Okay, plus oxygen gives you CO2 plus H2O. Let's balance this out. So this should be 4 and this should be 5. And we have 8 plus 5 here, that's 13, minus 1, 12. This should be 6. Okay, so logically, it should be 6 moles of oxygen are required for complete combustion. In which pair will each compound give a different visible result with aqueous, alkaline, iodine? So the iodoform test. So the iodoform test is positive for 4 types of compounds. So ethanol, we have methyl ketones and some secondary alcohols. With a methyl group as the side chain over here. So ethanol, both of them will give a positive result. So A is wrong. Ethanol, and this is propanone, methyl ketone. So both of them will be positive. This is ethanoic acid, and this is pentanthreone, which is not a methyl ketone. So this is negative, this is also negative. So C is wrong. Both of them are negative for the test. And for D, it is correct, because D, ethanol, which gives a positive result, won't be. So one is positive while the other is negative. Which reagent gives a positive result with propanone? CH3, COCH3. Aqueous alkaline iodine. This is in fact a methyl ketone. So yes, of course, A does give a positive test. These two are for aldehydes, not ketones. 35. Esters can be hydrolyzed with an aqueous alkali or an aqueous acid to form 2 products. The table compares the 2 methods. Which row is correct? So esters, for example, this CH3, CO, CH2, CH3, ethyl ethanoate. It can either react with aqueous alkali or aqueous acid to form 2 products. The table compares the 2 methods. Which row is correct? Aqueous alkali, complete conversion to a salt and an organic compound. So if we use an alkali like NaOH aqueous, what happens? This turns into a salt, CH3 COO minus Na plus, and we get the alcohol CH3 CH2OH. That is perfect. So yeah, we get an organic compound and a salt, correct. And if we used an acid instead, like HCl aqueous, dilute acid, we would get the acid CH3 COOH as well as the alcohol. Let's try to figure out what is wrong and why this isn't the correct answer. Like, what determines whether it turns into a complete conversion or whether it's in equilibrium. So the actual answer is, look, why is A wrong? Because if you give the alkali, you actually get a salt and an alcohol. Salt and alcohol, look, but they said complete conversion to salt and organic acid. This should have been alcohol, so this is wrong. So B forms an equilibrium mixture with salt and organic acid, wrong again. So it's between C and D, complete conversion to salt and an alcohol, and here forms an equilibrium mixture with an organic acid and alcohol, complete conversion to an organic acid and alcohol. So the general idea is it should be an equilibrium mixture, mainly due to the fact that ethanoic acid is a weak acid, so it won't actually fully dissociate, right? So we actually end up with an equilibrium mixture. So 35 should be C, okay? 36, structure isomerism only should be considered. How many compounds with molecular formula C5H11Br are primary halogen alkanes? Okay, let's start. Okay, C5, 1, 2, CH, okay, CH3, CH2, 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 CH2Br. C5, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, right? So I'm drawing this compound right here. 1, 2, 3, 4, 5. We have a Br over here. This is primary halogen alkane. Now let's do the branching. So I have Br again over here. Now let's do the branching. Okay, so 1, 2, 3. Now what I'm gonna do is, so 1, 2 1, 2, 3, 1, 2, 3, 4, 5. Okay, so I'm gonna put 1 over here, 4, and 1 side chain over here. So the first one was 1 bromopentane. The second one is 3 methyl 1 bromobutane. And then let's go again. 1, 2, 3, 4. This is 2 methyl rather than 3 methyl, which is 2 methyl 1 bromobutane. I'm just juggling this last alkyl group. And then let's go again. We have Br over here. So we have to make it primary, right? So this carbon over here, it has to be CH2. So this is carbon number 2. So we can have 3 side chains over here. Okay, like this. So this is 2, 2 dimethyl 1 bromopropane. This is the compound I drew. CH3, C, CH3, CH3, CH2, Br. Essentially, it's this compound CH33, C, CH2, Br. So in total, I'm getting 4 because I can't make any more primary from these. That's the essential idea. This is it. This is the end stage of primary halogen alkanes. So I'm gonna go with 36A. 37. Compound Z is formed by the reaction scheme shown. What is the formula of compound Z? So you guys know the drill. We have ethanolic cation. So this actually results in a nucleophilic substitution, CH3, CH2, CN. And after acidification, a nitrile has 2 routes, either acidification to form the carboxylic acid, or you could reduce it to form the amine. So after acidification with the acid, it turns into the carboxylic acid, CH3, CH2, COOH. So this is actually propanoic acid. We are looking for propanoic acid, so 37 is D. Last 3. Hydroxyethanol is heated under reflux with an excess of acidified K2 CrTO7 until no further oxidation takes place. Okay, so let's try to figure this out. CH2, CHO, and OH over here. So basically, this is a primary alcohol. So the primary alcohol will be converted to a carboxylic acid, and the aldehyde. So it turns into this first, CHO, CHO, and then the aldehydes also get oxidized to form a carboxylic acid. But this breaks down to form carbon dioxide, but they just want the skeletal formula of the organic product. So it should actually be D, which is COOH, COH, COOH, COH, COOH, COOH. Aldehyde gets oxidized to form carboxylic acid. Primary alcohol also gets oxidized to form carboxylic acid. 39. The formula shows the repeat unit of an addition polymer. What is the correct name of the monomer from which it is? I write C. I'm writing this C over here. 1H on top. So I just wrote it in a linear fashion. From the repeat unit, I figured out the monomer and then I wrote it in a linear fashion. 40. The infrared spectrum of a compound is shown. So which functional group could the compound contain? So essentially in IR spectroscopy, I plan to make a video on spectroscopy soon, dealing with IR spectroscopy, NMR, as well as mainly NMR and infrared spectroscopy, as well as mass spectroscopy. Anyway, you are supposed to look for a broad peak around 3000. If there is no broad peak, that means there is no hydrogen bonding. So basically, we are going to exclude everything here that has hydrogen bonding. So we get rid of alcohol and we get rid of the carboxylic acid, because I do not see a broad peak over here. Broad peaks refer to hydrogen bonding. And so we get rid of alcohol, carboxylic acid. It's between ester and nitrile. So the next peak you need to look at is around 1600 to 700. If you see a sharp peak over there, that means the CO group is present. In what exactly? Carbonyl, aldehyde, ketone, carboxylic acid, then ester, okay, then amide, CONH, these ones. However, since the compound does not have hydrogen bonding, this is excluded. So it is either between aldehyde, ketone, ester. Amide is also excluded, no hydrogen bonding. So it's between aldehyde, ketone, and ester. So let's look for the compound. Since we do have ester, the answer is C. And it is not nitrile, because look, if it was nitrile, we would get a peak at 2200 to 2250. There is no peak over there at 2200. So it's not a nitrile, it has to be an ester. Because look, for an ester, there is a peak at around 1700. A sharp, strong peak. They did not write that. It is usually present in the data booklet, but you need to know this. So I'll make a video soon on the tricks to solve an IR spectroscopy question. It's very straightforward. I can make you understand in 10 minutes basically. There are a lot of tricks. Anyway, that's been it. I also plan to launch a chemistry course soon at the end of this year, which will be available for purchase, where I talk about all topics in the syllabus. It's like a complete course. So more information on that soon. Anyway, we've solved the paper. I think it was relatively hard, the first 20, but afterwards it was a breeze. The organic ones were especially very easy. Hopefully I could explain everything in a concise and quick way. So quick shout out to my highest tier patron for the month, Tim. Very nice guy from Bangkok. He's going to study in the US soon. If you want to be featured on the end screen for all of my videos, please do consider supporting me on Patreon. It's patreon.com/CAIE papers solved, where you get access to all my notes and these solved papers for physics, chemistry, bio, as well as math, and access to one-on-one meetings with me on the highest tier. Anyway, I'll link the paper for May-June 2023, paper 1-2 up here, and the paper for February-March 2023, paper 1-2 down here, and I'll give a link for the chemistry paper 1 playlist up here. Remember to hit the subscribe button. See you guys. Bye bye.